So welcome back. So the next thing we're going to talking about is things that derive from what we've spoke about. We've talked about Fg, and that's the force that's felt by one object, under the influence of the gravitational field of another object. It turns out, so this is, if you like, this is the Earth, and this is my object, and there's my Fg, yeah? Supposing that I didn't put that object there, supposing that there was just that point in space, would there be any utility in ascribing, in linking some kind of gravitational effect to that point in space without an object there? So there's no force, but there's still, the Earth is still there. So let's go, rather than there, let's go around here. Similar position, let's go there, that point in space. We find it quite convenient to think in terms of the gravitational effect of the Earth on that point in space, even when there's no object there. So this is the grav force on a mass at point P, and this is the grav field at point Q, if you like. Yeah. I could turn around and say, what's the gravitational field at point P? And if I know the gravitational field, I can find out the gravitational force. So I'm going to call this grav field. That grav field is G. I'm sorry, is little g. This is little g. Now we learned that little g is 10 newtons per kilogram. But that's because we're always at the same distance from the Earth. We're always 4,000 miles from the middle of the Earth. That's where we do most of our mechanics, in a room. But if we were to go higher, we'd get a different value for little g. Go to the moon, it's 1.6, not because of the Earth, but because of the moon. It's like, there's an effect there. So different points in the universe have different gravitational field strengths. And it's useful to figure out what the different gravitational field strengths are, because you can always find that Fg is equal to m times little g. You've done that before, haven't you? You've said weight is equal to mg. What you were really saying was the gravitational force is equal to the mass of the thing that you're interested in times the gravitational field strength at that point. Now, I suspect you were taught it's the mass times the acceleration due to gravity. And that's not true. It gives you the right answer, but it's not the best way of interpreting what you just wrote down. What you just wrote down was it's the mass that you're interested in multiplied by the gravitational field strength at the point you're going to put that mass. And this is kind of interesting because later on you're going to go Fe is equal to Q times E. Now that looks much more impressive. That's saying that the electrostatic force is equal to the electrostatic charge times the electric field at the point where you put that electrostatic charge. So it's an analogous thing. And if we want to be a bit more involved, that is equal to that, just like that is equal to that. So vectors can come in for electric field, for gravitational field. Gravitational field is an imaginary grid going in space from all objects. And you can ascribe a value at any point on that grid which is the gravitational influence at that point. It's very abstract, but incredibly useful. And so when I was a student, I said, oh, I'm going to stick with forces because I get that. I'm going to blow all these fields off because I can always figure it out. And then I found we talked about field, and 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 we talked about field. We hardly ever talked about force again. So embrace it and struggle with it and kind of get comfortable with it. It's very abstract. It's this imaginary grid that goes out in all directions in space. And on each point on a scaffold, you can ascribe a number. And that number is the gravitational effect, gravitational field strength. Okay. Now, if I just play with this a little bit, if I know that Fg is equal to big G, big M, little m over r squared. Now I've got to be careful here. This is subscript G. That's not thing G. Yeah, that's just Fg. Let's join them together like that. You know. Then I can say, and I know that Fg is equal to m times G. Well, there's m, and there's m. So little g is equal to big G, big M over r squared. And I don't know what you feel about that. That is different but similar. When we compare these two equations, this is just in terms of magnitude. That is different but similar. And whenever you see things that are different but similar, be very wary of them. Put them down on a page side by side and try and compare and contrast. So we have, they're both inverse square relationships. If I go twice as far away from the planet, my gravitational field is 1/4 the strength. If I go 3 times further away from the planet, my gravitational field is 1/9 the strength. If I go 5 times further away from the planet, my gravitational field is 1/25 the strength. It's an inverse square relationship. But this only has the planet's mass in it, because there's no other mass put there. It's not about the second mass. It's about the planet. And we won't always deal with planets, but it's good to visualize planet and, you know, asteroid or something. Okay. So, in a way, and this is a bit of a, it's not a cheat, but it's I would get the same numerical value for my gravitational force and my gravitational field if the little mass was 1 kilogram. Yeah, because big G, big M times 1 over r squared is the same as big G times big M over r squared. If I cheat in a way and make this 1 kilogram, I get the same numerical value as the gravitational field. Agreed? So sometimes we say that the gravitational field is force per kilogram on object. And it's true. It's numerically equal to the force per kilogram on an object. But the problem is you don't need that object to be there. It's like it doesn't have to be there. The gravitational field exists because of the planet. There's also another gravitational field because of the object. It's a less intense gravitational field. But yeah, everything has a gravitational field around it. But it's best to picture this one way. Big planet, little object. You know, let's think about that, and we can always reverse things. Okay. And if you think about it, I get from the field to the force. How do I go from the field to the force? What do I do if you look at those two equations? I took big G, big M over r squared as the field, and what did I mathematically do to get the force? I don't do anything with big G, I don't do anything with big M, I don't do anything with what did I do to that expression to make it into the force? I didn't add, what did I do? I didn't subtract, what did I do? I multiplied by, didn't I? So if you want to go that way, you times by little m. And if you want to go that way, what do you think you're going to do? Divide by little m. Okay, so that's interesting. Okay. Okay. So let's talk about that. So we say gravitational field strength, little g. Gravitational field strength, little g, at a point in space is defined as the gravitational force per unit mass. There, I'm doing that little cheat already. That would be felt by an object if it were positioned at that point in space, but it doesn't have to be. It's about the planet. It's not about the mass you're choosing to put there or not. It is measured in newtons per kilogram, and it's a vector quantity. It points towards the Earth as far as the Earth is concerned. So we can say G, little g, is equal to big Fg over m. We can express the gravitational field strength in terms of the host mass, that's the planet, and the position of the point of interest by saying G is equal to big G, big M over R squared. And if I want to do it in terms of vectorially, I'd go, again, big G, big M over R squared times the unit vector. And there's my unit vector there. And there's the gravitational field, and the point in opposite directions, so that's where that minus sign gets justified. Yeah. Same scale, isn't it? Same kind of thing. So let's talk about the first bit first of all, because people get so wrapped up in the vector stuff they forget about the simple stuff. 8.2 kilogram block experiences a weight of 13.3 newtons when it is located in space near planet Zebron. What is the magnitude of the gravitational field strength G at that point in space? So here's planet Zebron, and I'm going to actually, there's my point in space. And I want to know my G at that point in space. So I go, well, little g is equal to big G, big M, over R squared for the magnitude. So G is equal to, G is what? 6.7 times 10 to the minus 11 times big M, 8.2. Oh, I'm sorry. No. 8.2 is that. I'm never given what big M is. Big M, I have no idea about. So that's not going to get me anywhere because I don't know what big M is. All I know is, I don't even know what R is, R squared is. So that's not going to get me anywhere. So what I say, well, that didn't work. But little g, sorry, I'm going to say Fg is equal to little g times M. Yeah. So little g is equal to Fg over M, which equals, 13.3 newtons over M, 8.2, which equals 13.3 divided by 8.2 equals 16, or 1.62. 1.62 newtons per kilogram. And the nice thing about multiple choice is if I was really stuck, that would tell me to take something that has force in it and divide it by something that has mass in it. And it only gave you two things anyways. That's why we don't do multiple choice, because it's like, I once had somebody walk into my, when I was at USF and I did multiple choice, I had somebody walk in, physics 1 student, and just in conversation, she said to me, well, your course is pretty easy. I said, what do you mean? And she goes, well, you just have to look at the equation sheet and pick out the equation. You don't even need to know the physics. I thought, well, you've got to be careful about that. And she goes, I don't think so. She said, I bet I could even do a decent job on physics 2. I had a physics 2 test right in front of me, so I gave her one. She did 3 questions. I've never got any of the materials. Just by writing down what parameters were given, guessing at the letters, because the letters are usually okay, and then looking for an equation on the equation sheet. And she got 3 questions, just boom, like that. And it was like, oh man, I'm not teaching physics. I'm teaching people how to substitute into an equation, and I think they walked in knowing how to do that. So that's one of the reasons why we got rid of that. Find the gravitational field strength G on the surface of the Earth. Oh, this is a little bit of a... This is kind of interesting. So here we have the surface of the Earth, and there's my point. And so what do I know? Oh, I know that G is equal to big G times the mass of the Earth over the separation squared. So G is equal to 6.7 times 10 to the minus 11 times the mass of the Earth. Well, I'm given the mass of the Earth. 5.98 times 10 to the 24 over. And then, I'm given the radius of the Earth. 6.37 times 10 to the 6, but that's got to be squared. So G is equal to, let's work this out. This is going to be 6.7 second EE to the minus 11, enter, times 5.98 second EE to the 24, enter, divided by parentheses 6.37 second EE to the 6. I wonder if I can do this. Squared. Let's see, I don't think it's going to let me do that, but no, it won't let me do that. So I'm going to go back, I'm going to put my parentheses, enter, and then I'm going to do that again, divided by 6.37 second EE to the 6. And hopefully that comes out to be 9.8. I'm cheating actually, my calculator just gave me a problem, but it's 9.8. So just check that over. 9.8, and it's going to be, let's have a look, it's going to be newtons per kilogram. Let's just have a quick look. 6 is a 12. That goes to minus 23. There's a 24. It's coming out, yeah? It's about right. Yeah, so check it. Check it. When you get home, check it. That's the number we learned. We learned that as 9.8. And that's where that comes from. So we've done FG and we've done G, and we know to go in that direction from we divide by a little m, and to go in that direction we multiply by little m. Yep. If I take a force and move it through a displacement, that is work. Work equals change in energy. If I don't have kinetic energy and I don't have spring energy, work equals change in potential energy. So F times D is equal to work, which equals delta UG. Just to remind ourselves of that. Oh, well, if this is FG times D is equal to work, which equals delta U G. Gravitation, I'm saying the same thing again, but this is using the force. So I have FG, I have G. If I multiply by D, I get delta UG. Yep. you can imagine if I divide by d. Really, it's multiplied by delta d, isn't it? And if I divide by delta d, I go backwards. Okay? I'm going to jump ahead a little bit. This will be in joules, and it will take, clearly you've got to have two masses, don't you? You need big M and little m, and you're asking what the potential energy is in that combination, yeah? I could become all abstract again and say, I wonder what the potential energy would be, potential energy difference would be if this was a mass of 1. What's the change in potential energy for 1 kilogram? And I would get delta V, like delta VG. And that is an abstraction. It's how much work you'd have to do raising 1 kilogram in space. Yeah. And then we come to that thing about, well, you can tell me the change in potential in going from the floor to the table, but can you give me a number for the actual potential energy of the tabletop? Not relative to the floor, but on some scale. I mean, we always measure things relative, pretty much, don't we? We measure mountains above sea level. We measure speed relative to the road. We forget that sometimes. We talk about the amount of speed in a car, half mv squared is kinetic energy, but relative to what? Relative to the road, relative to that aeroplane that's flying, relative to the sun? What? We forget we're doing a relative velocity. It seems like it's an absolute value, but it's not really. And so when people start thinking about the potential energy of a place in the space, then it's a little bit problematic. Because intellectually you'd say, well, rather than taking it with respect to the floor, let's dig a hole down as deep as we can go. So now I'm taking my potential energy relative to the center of the Earth. But really the sun's lower gravitationally. We fall into the sun. So the sun's lower than the center of the Earth is. And actually the middle of the galaxy is lower than the sun is because we fall into the middle of the galaxy. And the middle of the galaxy, well, it's the middle of the local group is lower than the middle of the galaxy, and we don't know where to go from there. So we can't find the bottom gravitational point. We have no idea where it is. We don't know how deep it is. We don't know what it is. So getting this absolute scale at first seems really problematic. We can talk about differences, fine, but bottom of the scale is really problematic. But then people have this idea of, I might not know where the bottom of the scale is, but I do know where the top of the scale is. I know that if I go sufficiently far away from all other masses, that the pull of gravity on that point, on that object is 0, I'm effectively as high as I can get gravitationally. I'm free. Let's call that 0. And rather than doing something weird, let's keep our ruler the right way up. So rather than having a ruler that starts at the bottom of the universe and goes to the top, so here's the top of the universe gravitationally, and here's the bottom. And rather than calling that and trying to get some number up here, maybe 260, why do we call this 0 and call this minus 260? A change like that is still positive on either side. You go from 100 to 110, that's plus 10. You go from minus 100 to minus 90, that's still plus 10. All you've done is you've literally took your ruler and slid it so the 0 is at the top rather than being at the bottom. And you have a whole bunch of negative numbers there, but it's still the same ruler. It's no big deal. It just looks really awkward. And if I do that, then I can talk about the potential energy at a point. And I can talk about the potential at a point. Not potential differences, but potential energies and potentials. And so that's kind of where we're going. Okay. The reason why I'm so keen on this is because when we do electricity, we're going to do exactly this again. So I want to try and give you as much as possible as I can beforehand. So there's terms, and you gotta be clear about this. There's grav force, grav field, grav pot n diff, grav pot n, grav pot diff, grav pot. 6 things, and they all mean something slightly differently, and it's easy to get them confused. So you've got to be, when I say anything with potential energy or potential, you've got to tweak up your ears. Is it potential or potential energy? Is it potential energy or potential energy difference? What is going on here? Because they mean something completely different, but similar. So let's have a look at this. So we say gravitational potential energy difference, so it's delta UG for a mass m that is moved from point P to point Q. So it is at point P. Here's a mass. There is a mass here, and here's a Q within the gravitational field of mass m. So big M's the planet. We've got this little backpack, and we're moving it through space. Want to know what's the change in its potential energy? We don't have to do it in a curvy way. We could just do it vertically upwards and vertically downwards. But, why not do it in a curvy way? We know that the work equals the change in potential energy, and that work is the integral of the change in force that moves through a distance. So delta UG equals minus integral of FR dr or Fx dx. And again, this is a thing, isn't it? It's not F times R, it's FR, yeah? It's F which changes as R changes. Yes? Most of this a lot of these problems come down to what do the symbols mean. So FR, this bit here, FR is a thing. It is minus G big M little m over R squared. We learned that before. So let's shove this through. So my change in potential energy is equal to minus the integral of minus G big M little m over R squared dr. Oh, I can integrate that. That's R squared with terms to, yeah, that's fine. Take your constants out. G, M, M. 2 negatives make a plus, so I've got positive in there. 1 over R squared dr. Oh, that's a piece of cake. G, M, M minus 1 over R. Remember, it's R to the minus 2, increase the power by 1. R to the minus 1, put it in the denominator, minus 1 over R, yeah? And it goes from whatever my first is to whatever my last is. The direction doesn't matter, it's just how far you are away. It's the radial separation that matters. So that comes out to be minus G M1 big M little m 1 over RF minus 1 over RI. Okay, so there we have it. RF is your final displacement, RI is your initial displacement. Let's play with this a little bit. Analogy. Well, actually, no, let's do it. So here's the planet, and here's my object. This is my initial, and there's my end, final. I'm going to take this mass, I'm going to move it like that. If I go up, if RF is bigger than RI, then that means I get a negative value for this. Can you see that? Something over 1 over something big minus 1 over something small is something negative. 1 over a quarter minus 1, no, let's not use that one. let's have a look. 1 over a third minus 1 over 2 is 2 over 6 minus 3 over 6, which equals minus 1 over 6. Yeah? When the final, because it's final minus initial, when the final distance is more than the initial distance, you end up with a negative on that bit. And that negative, with that negative, gives you a positive change in potential energy. And isn't that what you want, going from there to there? Shouldn't delta U be positive in going up in space? So the signs work out. Fortunately, you got to remember there's a negative sign in there, but the signs work out. There is a way of visualizing this, and I don't know if it's that helpful to you, but I'm going to show it because it's helpful to me. And that is that I tend to think of this in terms of volcanoes. And we have these contour lines. And I say, well, now let's draw this out the other way. That's what I just did. I said, let's go from there to there. That's a bit like saying I went from that point there. Oops, I did this the wrong way around. Let's go back. So let me just look at this again. So I'm going from there to there, from there to there. That's a small number. Oh, yeah, I'm sorry. Yes, that's right. I'm going up in potential energy. Yes. Oh, man, I did this last semester and I managed to catch it after I'd finished the whole thing. So let's look at that. In electrostatics, we have positive charges and negative charges. In mechanics, we just have holes. So we don't have mountains. We have gopher holes. So this could be, for example, this could be the map of the moon and the earth, if you like. Yeah? Because you're attracted into the hole. Yeah? You're attracted to the masses. You're not repelled by any masses. You're attracted into the masses. So in this case, I go from a point which is relatively close by to the hole to another point that is relatively far away from the hole. I do that. And you can already see that, well, I've gone up by that amount. There's my delta UG. And it seems so obvious when you think about it as climbing out of a hole. And that's what that previous thing was just telling you, okay? So try to link it back to, you know, just an imagination about holes and the like, and you'll get the sense of it. Okay, so there's a take-home equation. 80 kilogram mass is located at the origin, so there's my 80 kilogram mass. Determine the potential energy when a 5 kilogram change in potential energy. Determine the potential energy difference is the same as the change in potential energy. That's still delta UG. Potential energy difference. The difference in potential energy between the beginning and the end. When a 5 kilogram mass runs from a point, oh, I'm being really nasty here. I'm giving this IJK stuff and all the hairs on the back of your head are standing up because you're going, vectors already? But no, I'm just being really cute here. Well, that's going to be 2. And that's going to be 8. Oh, because the direction doesn't matter. So I say delta UG is equal to minus big G, big M, little m. It's not over r squared. What was it? 1 over r final minus 1 over r initial. Yep. Delta UG is equal to minus G. Let's just leave the G in. Big M is 80. Little m is 5. 1 over 8 minus 1 over 2. Delta UG is equal to minus G, 5/8 of 40, that's 400. 1 over 8 minus 4 over 8, which equals minus G 400 minus 3 over 8. Delta UG is equal to plus 5/8 of 40, so that is going to be 50 minus 150 G. It's going to be that guy. It's going to be plus, because that negative and that negative cancel, and this is going to be in joules. Whoops, joules. So not bad. Not bad. Yeah, not bad. Got to know the equation, not be put off by the different complicated ways I tell you the distance from the thing and just substitute in. Let's stop for a minute and just think about this. M1, M2 are included, but it's not a 1 over r squared relationship, it's a 1 over r relationship. Yeah. So the force had M1 and M2, big M, little m, but was a 1 over r squared. And the field had just big M and was a 1 over r. So this is similar to both of them. Again, similar enough to get them confused. So I'll put them down side by side. Let's go to the next bit, which is, okay, I'd like to know the absolute value for the potential energy inside an object when it's in the gravitational field of, say, a planet. I want a number for it. And so here's my planet, and here's my object, here's my mass, and I know a certain separation, and I want to know what the potential energy is. And what you do for this is you kind of say, well, hold on, I don't know where the bottom of the universe is, but I know where the top of the universe is. So I'm going to use my same basic equation. Change in potential energy is equal to minus G, big M, little m, 1 over r final minus 1 over r initial. And I'm going to say, well, I'm going to start off from infinitely far away when the value is 0. Because something minus 0 gives me the value of something. So what I do is I say, okay, I'm going to put infinity in for that. And so 1 over infinity goes to 0, and that just goes away. Yeah. So I go UG, not delta UG, now it's the gravitational potential energy, is equal to minus G, big M, little m, 1 over r, where r is that value. And here's a graph of it. This is UG versus my point, and there's my value of UG. At that distance from my planet, from the center of my planet, at that distance from the center of my planet, boom, there I am. Okay. Potential energy getting less and less and less as I get closer and closer, and getting more and more and more as I get further away. Going to 0. When you're infinitely far away, you have no potential energy. I know it just seems wacky because we moved our number line. So now I have negative potential energy. I have negative potential energy. I have a bit less negative potential energy. It's a positive change. I just moved my number line. And that's just incredibly uncomfortable. But it's true. Notice this equation. It's got big M, little m, not a 1 over r squared relationship. It's a 1 over r relationship. 80 kilogram mass is located at the origin. There's an 80. Determine the potential energy of a 5 kilogram mass located at there, 5. I say, what I say is I say delta UG is equal to minus G M 1 over r final minus 1 over r initial. Delta UG is equal to minus, UG is equal to GMM 1 over r final minus 1 over infinity, which equals minus GMM over R. So UG is equal to minus G, big M is 80, little m is 5 over 2, which equals minus 200 G joules. Minus 200 G joules. Minus 200, yeah, G joules. Cool? Cool. You look at that. What is the gravitational potential energy of a 5 kilogram mass that is located at 70. 2I plus 3J plus 1K meters. 5. 3I plus 2J plus 4K meters. What is the gravitational potential energy of that guy? So it's going to be UG is equal to minus G, big M, little m, over R. So UG is equal to minus G, big M is 70, little m is 5 over R. Oh! There's my R. R's the separation, isn't it? Yeah, there's my R. I've got to find that separation. So here's a little bit on vectors. Doesn't matter which way round I do this. I'm going to say the vectors like that. I'm going to say that that's R. I'm going to say that this is R1 and that's R2. I'm going to say that R1 plus R is equal to R2. Do you see that from my diagram? It's not R2 plus R equals R1. It is R1 plus R equals R2. And it's because of the arrowheads. The process of addition in vectors is you put the tail of the tail of the second on top of the head of the first. And so that's been added, but that's not. So it's R2. I'm sorry. Then I went and did it wrong. R2 plus R is equal to R1. That guy there, which is R2, plus that guy there, which is R, is equal to R1. Yeah? So R is equal to R1 minus R2. Yep. So R, let's do IJK. So R1 is going to be 2, 3, 1. R2, let's call it minus R2, is going to be minus 3, minus 2, minus 4. We've got to add those two guys together. Add. So we're going to get minus 1 plus 1 minus 3. So this vector here is that vector there. So that means that R is equal to the square root of minus 1 squared plus 1 squared plus minus 3 squared. So R is equal to 1 plus 1 is 2 plus 9 is 11, the square root of 11. So that means that UG is equal to minus G, 7 fives are 35, 7 fives are 35, 350 over square root of 11. If I did that right, 350 divided by second square root 11, I'm getting 105.5 G, so it'd be equals minus 106 G joules. So it's same old, I'm just bringing in some vectors to make it, you know. Visualization. It's visualization. Okay? Now, next step. All right. Let's say that the mass we're playing with, not the planet, but the mass, is 1 kilogram. Okay. Then I simply get that if UG equals minus G, M, big M, little m over R, and little m equals 1, I get the gravitational potential is equal to minus G, big M, times 1 over R. And that's what that is. It is an abstraction. It's like electric field. So, is that about it? I got just a little bit more. So, a 3.6 kilogram block has a gravitational potential energy of that when located near planet Zebron. What is the magnitude of the gravitational potential at a point? So, here's my block. So my little m is equal to 3.6 kilograms, and my gravitational potential energy, that is UG, gravitational potential energy, UG, is equal to minus 43.7 joules. What is the magnitude of the gravitational potential? VG equals that. And I know that VG is equal UG over M, just like I knew that that little g is equal to FG divided by M. Yeah? So VG is equal to minus 43.7 over 3.6. So VG is equal to whatever that works out to be, a number. 43.7 divided by 3.6 is equal to minus 12.138. Minus 12.138. And the units are going to be joules for every kilogram. Last little bit. So a 60 kilogram mass is located at the origin. What is the gravitational potential? That is my VG at a point that is located 5 meters away. I say VG is equal to, what was it, minus M minus G, M over R squared, over R, man, shame on me, minus G, M is 60 over R, 5 which equals minus 12g joules per kilogram. What are you responsible for? Being able to use the equations. But I do find it's really useful to be able to get the overview. So let's go back. FG, G. And we can say, well, if we want to go from there to there, we divide by little m. Want to go from there to there, we multiply by little m. Delta UG. Want to go from there to there, multiply by delta D. Want to go from there to there, you divide by delta D. Delta VG, that is the energy per kilogram. Change in energy per kilogram. Want to go from there to there, divide by m. Want to go from there to there, multiply by m. Yeah. You want to go from there to there, multiply by delta D. Want to go from there to there, divide by delta D. And alternatively, it's analogous, but it's kind of like to show my UG and my VG, I got to take this value and I'm sorry. I got to have infinity as one of my points. It's not, that's where I struggle with this. I can't give you an easy division or multiplication because you've got to do that thing where the other point is infinitely far away. But what I can do is I can tell you that this is FG is equal to big G, big M, little m over R squared. And I can tell you that G is equal to big G, big M over R squared. And I can tell you that that is going to be, so my delta UG is going to equal big G, big M, little m, 1 over R final minus 1 over R initial. And I can tell you that delta VG is equal to big G. The difference between these two is we don't have that M in it. And I can tell you that UG is equal to big G, big M, little m, 1 over R final, or 1 over R if you like. And VG is equal to big G, big M, 1 over R final. There's my 6 equations. And the way I'm able to write them down so easily is I can see the pattern. And the pattern is big M, little m, big M, little m, big M, little m. Only big M, only big M, only big M. R squared, 1 over R squared, 1 over R squared, 1 over R, 1 over R. And then if I want to go from there to there. So it's really useful. So I used to teach this And every semester people would just fall apart with it. And it got very frustrating. And one day I said to my wife, this is so annoying. You know, I've been teaching this for so many years and they're still not getting it. And she said to me, they've only been there for a few weeks. You've been teaching it for this many years and you're still not teaching it. You know? And she's right. And I went to a teacher training class from USF, and there was a guy talked about student-centered learning, and we got onto a conversation about critical thinking. And the big joke is, in physics, we always say we had critical thinking because one of the hallmarks of critical thinking is problem solving. And we have thousands of problems that we solve. But is that what they mean by problem solving? I think they mean not doing math. I think they mean solving problems. Well, this is that, and that's that, and what do? We learn how to do set examples. We kind of teach you, here's the problem, learn how to do it. Here's another problem, learn how to do it. We don't give you things you've never seen before. That's real problem solving, when you've never seen it before, and then suddenly faced with it. We don't test that so much. So I was a little bit concerned about that, and I talked to the instructor. I said, I don't believe we do really much critical thinking when I think about it. What's the real hallmark of critical thinking? Because I think the best way of critical thinking is you look for comparison, compare and contrast. When you're saying compare and contrast, you're really getting the students to think critically. And this light went off in my head, and I came home, and it was like, yes, I think I have a better way. And the better way is to get you to look at this and compare and contrast. And be clear, your job is to know what the different things are in words. I'm not above asking you for that. Define for me gravitational field. Can you say it in words? And then, does the gravitational field follow an inverse or inverse square relationship? If you know the equation, it's clear. Can you write down these equations? You're responsible for those equations. Can you write them down? And you know, if you remember all 6 of them, good luck to you, but I don't. I kind of remember that, and I can figure this out. If I can figure that out, I can figure this out. If I can figure that out, that's easy, and then that's easy, and that's easy. I know one equation, I can figure out the rest. This is really important, because when we get to physics 2, we spend about 4 classes doing this with electrostatics. It's a little bit harder because there's attraction and repulsion in electrostatics, but in principle it's this. Okay? So for sure, I'm going to give you write for me the expression for the force felt by this mass, like we did that example. That's for sure going to be that. But then expect something from these other things to come. And it's plug and chug. You know, if you know the equation, it's straightforward. But beyond that, deeper than that, I'd like you to get to the stage where you bring it together. You recognize there's a significant advantage to you if you can bring this together and you master it rather than it mastering you. Because if you can, you set yourself up for a relatively easy stretch of physics 2. Because it's the same thing, just in electrostatics, okay? So let's call it a day there. Oh, so this next bit, let me show this next bit. I never get to this bit because I'm always a bit behind. This next bit is escape speed from a planet, and basically what it says is that for any planet of a given size and a given mass, there will be an escape velocity, and that is the velocity you'd have to give a cannonball to enable it to escape the gravitational pull of the planet. It's not talking about rockets. It's talking about projectiles. And to that extent, you know, NASA does not use projectiles, it uses rockets. So to that extent, it's got some limited value. But, and it's, you know, it's there. I've not got much interest in it. I don't do an example of it. So we'll call it a day there.